differentiate f of x equals 2x minus 3 raised to the fourth power times x squared plus x plus 1 raised to the fifth power. You might already be able to tell that this one's going to be a little bit more work. We have a product of two functions, so we're going to have to use the product rule, but each of those functions is a composition of functions, and so we're going to have to use the chain rule for each part of the product rule that we use. So let's go through this very carefully. If we want to differentiate this, we've got to use the product rule. And the product rule says that we take the derivative of the first part. So that's going to be the derivative of 2x minus 3 to the fourth power times the second factor, x squared plus x plus 1 to the fifth, plus the derivative of the second factor. So that's going to be the derivative of x squared plus x plus 1 to the fifth power times the first factor, which is 2x minus 3 to the fourth. So all we've done so far is written out what the product rule gives us. The derivative of the first factor times the second, plus the derivative of the second factor times the first. And then with the two derivatives that we have now, each of those is going to require using the chain rule because each one of those is a composition. So let's look at those one at a time. For this first one, we're differentiating 2x minus 3 to the fourth power. That's basically u to the fourth. The derivative of u to the fourth is 4 times u cubed, or 4 times 2x minus 3 cubed, times the derivative of the inside. The derivative of 2x minus 3 is just 2. And then that is multiplied by x squared plus x plus 1 all to the fifth. And then plus, we've got to use the chain rule again for this second part. The derivative of u to the fifth power is going to be 5u to the fourth. So we've got 5 times x squared plus x plus 1 to the fourth times the derivative of the inside. The derivative of x squared plus x plus 5 is 2x plus 1. That's what we get when we use the chain rule. And then we also have times 2x minus 3 to the fourth power. Oh boy, there is a lot going on here. And we don't want to leave it like this. This is kind of clunky. We have two options. One of those options is to multiply out all of these different polynomials and expand it all out and combine like terms and get one monster polynomial. I don't love that idea because that's going to be a huge polynomial. The other is to see what these two terms have in common and factor that out and see what we get with the leftovers. And I like that a lot more. So let's start and see, what do these two polynomials have in common? I'm actually going to put this in blue. We don't need to do this in a different color. I just think there's a lot going on, and so maybe using multiple colors might help. If we look at these two different terms separated by the plus in the middle, we can see that they both have powers of 2x minus 3, and they both have powers of x squared plus x plus 1. So let's write what they have in common. They both have powers of 2x minus 3, and one of them has 3 factors of that, and the other has 4 factors of that. So what they have in common is 3 factors of that. And then they also have powers of x squared plus x plus 1 in common. The first one has 5 factors of that, and then the second one has 4. So in common, they have 4 of those. So that is the greatest common factor between those two giant terms. And if we pull those out, let's see what's left in each of them. In the first one, if we pull out 2x minus 3 cubed, that gets rid of that whole bit, and we're left with 4 times 2, which is 8, times Now we had 5 factors of this, but we pulled out 4, so there's 1 factor of that left. So remember we said 4 times 2 was 8, and we had 1 factor of this left, so x squared plus x plus 1. Plus, let's look in the second group and see what's left over. We've got the 5, that's pretty easy. And then if we look, we had 4 factors of x squared plus x plus 1, but we pulled all those out, so that all goes away. And then also 3 of these 2x minus 3's were pulled out, so that leaves 1 factor of 2x minus 3 left, and then the other factor of 2x plus 1. So we've got 2x plus 1 times 2x minus 3. And what I want to do is I want to multiply all of this out and expand it and see what we end up getting, because it might be that there's another one of these factors that we could factor out. Basically, there might be something that can be factored more. And since all of these bits are neatly factored, it would be nice to be able to neatly factor those bits. So we're going to not touch these things out front. These are going to stay like this for the rest of the problem. And then in here, if we distribute the 8, that gives us 8x squared plus 8x plus 1. And then if we look at what's going on in here, I'm going to FOIL this out, but because we've got the 5 out front, as I'm foiling, I'm going to multiply each of these products by 5. So the first term's 2x times 2x, that's 4x squared. But if we multiply that by 5, that's going to be 20x squared. Then the outer ones, 2x times negative 3 is going to be negative 6x. But when we multiply that by 5, that's going to be negative 30x. For the inner terms, 1 times 2x is 2x. And when we multiply that by 5, that gives us 10x. And then the last terms, 1 times negative 3 is negative 3. But if we multiply that by 5, that gives us negative 15. And then we can combine like terms in the brackets. So we've got 2x minus 3 cubed times x squared plus x plus 1 to the 4th. And then if we combine like terms, the x squared terms, 8x squared plus 20x squared, gives us 28x squared. If we look at the linear terms, let's see, 8x plus 10x is 18x, but then 18x minus 30x is going to be negative 12x. And then if we look at the constant terms, 1 minus 15 is negative 14. We can factor out a GCF of 2 from in those brackets. Let's do that now. So we've got a 2 that we can pull all the way out front, times 2x minus 3 cubed times x squared plus x plus 1 to the 4th. And when we factor out a 2, that leaves us with 14x squared minus 6x plus 7. Now, you could try and use the AC method to factor this. You could even use the quadratic formula if you wanted to get an idea of what the factors might be, but in the end, this does not factor nicely. I think we require complex numbers there. So this is as broken down as we can get it, and that final derivative is going to be 2 times 2x minus 3 cubed times x squared plus x plus 1 to the 4th times 14x squared minus 6x plus 7. This is one of the nastiest ones we've looked at so far, and that's because when we have the product rule and the chain rule multiple times, we end up, particularly with polynomials, with loads and loads and loads of terms. And if we want to put it in any nice way where things are factored, it's going to take a fair bit of algebraic manipulation. So unfortunately, some of these are going to be heavy problems and take a fair bit of time.